In this lecture video, we're going to learn how to test a claim about a population mean. As we get started, let's review the steps of hypothesis testing and make sure that we understand correct notation. The first step is to identify the null and alternative hypotheses. The second step is to calculate the test statistic. The third step is to calculate the p-value or critical value, depending on which method you choose. And the last step is to determine and state the conclusion. Lowercase n is our sample size, lowercase s is the sample standard deviation, x bar is the sample mean, and mu sub x bar is the population mean that we'll take from the claim and use in the null hypothesis. When testing a claim about a mean, we have two scenarios. One option is that we might have a value for the population standard deviation. That is, sigma is a known value. In that case, our test statistic is a z, and we calculate it using this equation here. Or we can use the calculator function z-test. A more common scenario is that we do not have a value for the population standard deviation. That is, sigma is an unknown value. In that situation, our test statistic is a t-value, and we calculate it using this equation. We can also find it by using the calculator function t-test. Let's get started with an example. Listed below are the lead concentrations measured in micrograms per gram that were measured in a certain type of medicine manufactured in the United States. We're going to use a 0.05 significance level to test the claim that the mean lead concentration for all such medicines is less than 14 micrograms per gram. The key information in this example comes from the last sentence. Here we find that the claim is that the mean lead concentration is less than 14 micrograms per gram. Writing this symbolically, we would have that the mean is less than 14. Now let's take a look at the sample data that we are given. One thing that's important to note is that nowhere in this example are we given a value for the population standard deviation. That is, sigma is unknown. That means our test statistic will be a t-value, and it will be important that in our calculators we use t-test and not z-test. Since we're given our raw data values, the individual data items, and not summary statistics, let's put these values into our calculators in a list so that we can calculate the summary statistics. Going to Stat, Edit, we can clear out any old lists and enter our 10 data values. Now that we have our data values in list 1, we can go to Stat, Calculate, one variable statistics. Entering list 1 as our list and pressing enter on calculate, we have our summary statistics. Our sample has a mean of 11.05 and a standard deviation of 6.46. Summarizing our sample data, we have 10 data values, so that's our lowercase n. We have a sample mean of 11.05 and a sample standard deviation of 6.46. Notice that I rounded to one more decimal place than what was given with the raw data. Now we'll list out the null hypothesis, H0. It's a statement of equality, and we'll grab the 14 from the claim. So our null hypothesis is that mu is equal to 14. Our alternative hypothesis, H1 then, is mu is less than 14, taken from the claim. From this we can tell that this will be a left-tailed test. And we also know that our significance level, alpha, is equal to 0.05. There are two ways to calculate the test statistic. We could use the equation t equals the sample mean minus mu divided by the sample standard deviation over the square root of n, or we can use our calculators. Using this equation and substituting our values, we have a test statistic t equal to negative 1.444. If we instead wanted to use our calculators, we would use t-test, and this is what that would look like. We would head to the Stat menu, toggle over to Tests, and find that t-test is the second option. In this situation, we were not given summary statistics. We were given the raw data, and we already have that in list 1. So we'll select Data. For the population mean found in the null hypothesis, we have 14, and our data is in list 1. We also have a left-tailed test, so we want to make sure to select less than mu naught. And pressing enter on calculate, we are given a test statistic t equal to negative 1.444 and a p-value of 0.0913. Notice that this also gives us the sample mean of 11.05 and the sample standard deviation of 6.46. From the t-test, we were given the p-value of 0.0913. And in order to state our conclusion, we can simply compare the p-value to alpha. With a p-value of 0.0913 and alpha equal to 0.05, we find that our p-value is greater than alpha, and we fail to reject the null. A concluding statement might read something like this: there is not enough evidence to support the claim that the mean lead concentration is less than 14 micrograms per gram. Alternatively, we could also use the critical value method. That would involve finding the critical value, and the critical value would be the t-score that has a left area of 0.05. All of these methods that I've mentioned are completely equivalent and give you the same conclusion. Now let's change the situation just a little. Suppose in the last example that we actually knew the population standard deviation sigma was 6.46120937. Does the knowledge of sigma have much of an effect? Let's find out. Now that sigma is known, our test statistic and critical values will be z-scores, and using our calculator, we will use z-test instead of t-test. The claim remains the same, and our sample data is the same. We also have the same null hypothesis of mu equals 14 and the same alternative hypothesis that mu is less than 14. The game changes as soon as we get to step 2. Now our test statistic is a z-score, and calculated by hand, we would use x bar minus mu sub x bar divided by sigma over the square root of n. And we would use the population standard deviation that was given to us instead. Filling in our values, we will again get a test statistic of negative 1.44, rounding to 2 decimal places because this is a z-score now. What changes is that we will look at the z distribution, not the t distribution. Let's take a look at this on our calculator. With sigma known, we no longer want a t-test, we want z-test. So heading back to the stat menu and toggling over to tests, we want the first option for z-test. We still have our data in list 1, so we'll select data, not summary statistics. The mean in the null hypothesis is 14, and the population standard deviation this time is given to us. This is also still a left-tailed test. And pressing enter on calculate, we now have our z-test values. We have our test statistic, z equal to negative 1.44, and our p-value of 0.0744. We're also given the sample mean and sample standard deviation. From running our z-test, we were given the p-value 0.0744. If you take a look at your z distribution table, you'll find a slightly different p-value, 0.0749. And that's also perfectly acceptable and will give you the same conclusion in the end. Now we'll determine our conclusion by comparing the p-value and alpha. With a p-value of 0.0749 and alpha equal to 0.05, we still have that our p-value is greater than alpha, and we still failed to reject the null. So, did the knowledge of the population standard deviation have much of an effect? Not in this case. Our p-value did go down some, which made it closer to alpha than before, but it did not change our overall conclusion. As a quick point to check for understanding and to catch all of those that might prefer to use their table and critical value method, let's add these values to our picture. Our alpha, or significance level, is 0.05. So the area in this far left tail is equal to 0.05. And the z-score associated with this left area is the critical value. Using your t-distribution table or the INV norm function in your calculator, we find this critical value to be negative 1.645. On the other hand, we calculated a test statistic of negative 1.44, which is not as extreme as our critical value. So it naturally has a left area larger than alpha. Its left area is the p-value, 0.0749. So in comparing the test statistic to the critical value, we find that the test statistic is not as extreme as the critical value, and we fail to reject the null. And if we compare the p-value to alpha, we find that the p-value is larger than alpha, and we fail to reject the null. That concludes this lecture video on how to test a claim about a population mean, paying special attention to the scenarios when we do and don't have the population standard deviation.